Every galaxy we see is moving away from us, and they're moving fast. This fact, this expansion of the universe, it breaks something. It breaks one of physics' most trusted rules. It breaks gravity itself. So by the end of this, you'll understand why this cosmic puzzle threatens to overturn everything, our entire picture of reality. We're going to confront a universe dominated by something mysterious, dark energy, and we're going to question whether Einstein himself might have been wrong. How do you picture the ultimate fate of everything around you? We see this tapestry of galaxies, hundreds of billions of them. That's our observable universe. For most of history, we thought this stage was fixed, eternal. The stars were just there, unchanging, a permanent backdrop. Then, in the 1920s, an astronomer named Edwin Hubble changed everything. He measured light from distant galaxies, and he noticed something strange. Their light wasn't the right color. It was stretched, shifted toward red. This redshift meant one thing. Those galaxies were moving away from us, and the farther away a galaxy was, the faster it was receding. That was the discovery. Space itself wasn't static. It was stretching, expanding in all directions, carrying galaxies apart. Think of raisin bread baking. The dough rises. Every raisin moves away from every other raisin. From any single raisin, all the others are retreating. We are that raisin, looking out at a universe where every other galaxy is sailing away on expanding space. This observation led to a new idea. If the universe is expanding now, then rewinding the clock means it was once unimaginably small, hot and dense, a singular beginning. The Big Bang that became the new cosmic story, a story of birth and growth, but woven into that story was a single, troubling thread, a subtle assumption about how this expansion should behave over time. And that assumption was about to shatter. That subtle assumption was gravity. It's what holds you to the Earth, what keeps the moon in orbit, what sculpts galaxies from cosmic dust. The architect of the universe, and for most of our history we thought we understood it. Isaac Newton gave us a law, a beautiful equation. It worked perfectly for everything we could see. But then came Albert Einstein. He saw gravity differently, not as a force, not in the way we normally think. He saw it as geometry. Imagine the universe as a vast, stretchy trampoline. That's space-time, a single fabric weaving together the three dimensions of space with the one dimension of time. Now place a heavy bowling ball in the center. The fabric sags. It creates a deep, smooth depression. That's what mass does to space-time. It warps it. Now roll a marble across the trampoline. It won't travel in a straight line. It'll curve inward, spiraling toward the bowling ball. The marble isn't being pulled by a mysterious force. It's just following the straightest possible path along a curved surface. That's Einstein's general theory of relativity. The planets orbit the sun not because the sun pulls on them, but because they're rolling along the curved grooves in spacetime that the sun's mass creates. This idea was revolutionary, and it was spectacularly right. It explained tiny quirks in Mercury's orbit that Newton's gravity could not. It predicted that light itself would bend around a massive star. A prediction confirmed during a solar eclipse. It gave us the theoretical blueprint for black holes, places where space-time is curved so infinitely that not even light can escape. For nearly a century, general relativity was the ultimate rulebook for the cosmos, gravity's grand design, elegant and unshakable. Yet when Einstein first applied his equations to the entire universe, he faced a problem. His beautiful geometry predicted a dynamic cosmos, one that should either be collapsing inward under its own gravity or flying apart. But the scientific consensus of his time, including his own belief, was that the universe was static, eternal and unchanging. So Einstein did something uncharacteristic. He added a fudge factor, a mathematical term he called the cosmological constant. Think of it as a kind of anti-gravity, a repulsive energy woven into the fabric of space itself. It perfectly balanced the inward pull of gravity, creating a static, stable universe in his equations. He later called this his greatest blunder, but the universe, it seems, has a sense of irony, because that very blunder, that cosmological constant he tried to erase, would return decades later. It would become the centerpiece of our greatest cosmic mystery, and its return would begin with a single, impossible observation: that gravity, as we knew it, was failing. For a long time, we thought the universe had a few possible endings. We had Einstein's equations, we knew about the expansion, so we could finally ask what happens in the end. It all came down to a kind of tug-of-war. On one side, the momentum from the Big Bang, still pushing everything outward. On the other side, gravity, the pull of all the matter, every star, every bit of dust. If there was enough matter, gravity would be strong. It would slow the expansion over billions of years, maybe stop it completely, and then reverse it. Everything would rush back together, space would contract, the universe would collapse in a big crunch, one big cycle. But if there wasn't enough matter, gravity would be too weak. The expansion would never stop, it would just go on forever. Galaxies would drift apart, stars would burn out, space would become a dark, empty void. A slow fade, the big freeze. So to know our fate, we had to weigh the universe. We started counting everything, every star, every gas cloud, all of it. We added up all the mass that could provide that gravitational break, and the answer was shocking. It wasn't nearly enough. The visible matter, the stuff that glows, was only a tiny fraction of what was needed to hold galaxies together, much less stop the expansion. That was the missing mass problem, but we thought there must be more matter we can't see. Planets, cold gas, faint stars, black holes. We called it dark matter. And for a while, that seemed like the answer. Dark matter would provide the extra gravity, the missing weight. It would be the break. The search for it became a huge quest. But as we looked closer, something stranger started to appear. The universe wasn't just hiding mass, it was hiding something much more unsettling. The real shock wasn't what was slowing the expansion down. It was the growing suspicion that nothing was slowing it down. In fact, the expansion seemed to be doing the opposite. The universe wasn't slowing down. It was speeding up. That was the finding. In the late 90s, it won a Nobel Prize. It completely overturned cosmology. Two teams of astronomers were looking out into deep space. They were using a particular kind of exploding star as a measuring tape. Type 1, a supernova. They're remarkably consistent. They always explode with about the same brightness. So if you know how bright something really is, you can tell how far away it is by how dim it looks. These teams were looking at supernova in galaxies incredibly far away. Which means they were looking back in time. They were measuring how fast the universe was expanding billions of years ago to compare it to the expansion rate today. The expectation was clear. All the matter in the cosmos, both seen and unseen, has gravity. That gravitational pull should have been acting like a brake. The expansion should have been slowing down over time, so the most distant supernova from the younger universe should have appeared a certain brightness based on that model of deceleration. But they didn't. They were fainter, much fainter, which meant they were much farther away than anyone predicted. The only way to explain that extra distance was if the expansion wasn't slowing down. It was accelerating. The fabric of space itself was stretching faster and faster as time went on. Think of it like throwing a ball straight up into the air. You watch it rise, you expect gravity to slow it, stop it, bring it back down. But instead, the ball keeps going up, and it starts shooting away faster and faster. As if the Earth itself were pushing it away. That's the scale of this discovery. It defied every intuitive understanding of gravity. A force that pulls was being overpowered by something that pushes. On the grandest scale imaginable, the comfortable model was shattered. The model of a decelerating universe, a simple cosmic tug of war between the Big Bang's momentum and gravity's pull. Physicists were left staring at their equations, forced to confront an unknown, repulsive force woven into the vacuum of space itself. They needed a name for this mystery. They reached back into history. They revived a term from Einstein's own notes. They called it dark energy. Dark energy is just a name for our confusion. It's the main suspect. To explain why the expansion is speeding up, scientists went back to an old idea that had already suggested something like this could happen. They looked at Einstein's old notes. They brought back his biggest mistake, the cosmological constant. But this time, it wasn't a trick to keep the universe from moving. It was the thing making it fly apart. This constant isn't something you can touch. It's not a particle. It's a property of empty space itself, a sort of latent energy in the vacuum. You can think of space as an active material with a kind of built-in spring, a tension that pushes outward. And here's the strange part. As the universe expands, it makes more space. More vacuum, and if every new piece of vacuum has this same intrinsic energy, then the total amount of dark energy goes up as the cosmos gets bigger. More space means more repulsion. The force doesn't get weaker over time, it gets stronger. It's an anti-gravity engine that fuels itself. That's why the expansion is accelerating. The push isn't just winning against gravity's pull, it's gaining strength while gravity weakens. The numbers are huge. When we measure all the energy in the cosmos, dark energy makes up about 68%. Nearly 7/10 of everything is this repulsive property of nothing. Ordinary matter, stars, planets, us is less than 5%. Dark matter, the invisible scaffolding, is about 27%. We live in a universe ruled by an enigma, a placeholder for what we don't know. We call it dark energy because we don't know what it is. Is it really constant like Einstein first thought? Or could it be a dynamic field that changes like a cosmic weather we can't read yet? Could it be a new fundamental force or a sign that Einstein's theory of gravity is incomplete on the largest scales? It's the leading idea because it fits the data, but it raises more questions than it answers. We've named the shadow, but we haven't seen what's casting it. What if the question itself is wrong? Instead of some new invisible substance, maybe the problem is with our most trusted law, gravity. Maybe gravity works differently than Einstein said. This isn't fringe. A lot of physicists and astronomers think the crisis isn't a lack of matter, but a misunderstanding of the force. They want to modify gravity. The main idea for that is called modified Newtonian dynamics, MND. It starts with a simple observation. Gravity from a star or a planet gets weaker with distance. We know that, but MND suggests that in the realm of extreme weakness, out at the edges of galaxies where the pull is almost nothing, the rules change. Newton's law, Einstein's refinement, they might just break down there. In those quiet outskirts, gravity could become slightly stronger than our equations say. Just enough to hold a fast galaxy together without any extra, invisible glue. Just enough to mimic the effects we blame on dark matter. For its supporters, MND is elegant. It removes the need for a mysterious, undetected particle. It explains certain stubborn observations perfectly, like the precise way stars orbit inside many galaxies. Under standard gravity, those stars should be flying off. Dark matter is brought in to provide the extra anchor, but under MND modified rules, the motion you see is exactly what you'd expect. The math works, no unseen substance. It feels cleaner, more direct, but elegance has a cost. While MND solves the galaxy rotation problem, it stumbles with the full cosmos. Its biggest challenge is the oldest light in the universe, the cosmic microwave background. That faint afterglow of the Big Bang is a snapshot of the infant cosmos. Its pattern of hot and cold spots is a precise record of how matter was clustered. The patterns we see are perfectly explained by a universe with ordinary matter and a lot of dark matter, all under Einstein's gravity. And in its original form struggles to reproduce that detailed fingerprint. It also has a harder time with the bullet cluster. Two galaxies collided. Their visible matter got separated from the gravitational bulk, which seems to have sailed right through. That looks like a direct map of invisible dark matter. A ghostly outline that modified gravity theories find difficult to sketch, so we're left with a stark divide. On one side, the majority view, keep Einstein's theory of gravity intact, but fill the universe with two unknown, invisible components. Dark matter and dark energy, together they make up 95% of everything. On the other side, a vocal minority, keep the universe made of the familiar stuff we see, but rewrite the foundational laws of physics. The laws that have guided us for a century. It's a battle between inventing new contents for the cosmos and inventing new rules for it. That's the core of the modern crisis. Our most precise measurements have led us to a cliff edge. We have to decide which leap of faith is more believable. Do we live in a universe dominated by shadows, or have we been reading gravity's manual wrong all along? 95% of the universe is unknown. That's not an exaggeration. That's the actual balance sheet right now. So if you take stock of everything you've ever touched, seen, been made of, every star, every planet, every grain of sand, all of that is ordinary matter. Atoms from the periodic table and all of that together, all that complex stuff, it's just 5% of the cosmos, 5%. It's the smallest slice. Then there's the next slice, about 27%. That's dark matter. We can't see it. It doesn't glow, doesn't reflect light, doesn't seem to interact with light at all. But we know it's there because of its gravity. Its pull is what holds galaxies together, keeps them from flying apart. It's like the hidden scaffolding the visible universe is built on. We feel its weight in how stars move, how light bends, but its true identity, it's still a ghost. And then the majority, the remaining 68%. That's dark energy. It's not matter. It's a property of space itself, a kind of pressure that's making the universe expand faster. It's the dominant thing, and we understand it the least. We only know it by its effect. It's pushing everything apart faster and faster. So you add it up, the familiar world, atoms, that's 5%, dark matter, 27, and dark energy, 68 together, that's 95% of everything. For all our knowledge, all the beautiful equations we've written, they only describe that tiny sliver, that 5%. We've mastered the rules for 5% of reality. The rest is still a map with blank spaces. That makes the search for dark matter and dark energy the biggest detective story in science. Every new telescope image, every measurement of distant supernova, every map of the ancient cosmic background radiation, it's all a clue. We're piecing together the nature of the cosmos from indirect evidence, trying to understand these invisible actors that shape everything. It's a reminder, really. The universe is far stranger, far more mysterious than we imagined. Our story isn't complete. We're still reading the first page. We have a photograph. A picture of the universe as a newborn. It's the cosmic microwave background, our most important piece of evidence. In the beginning, the universe was an opaque plasma. A hot soup of particles and light, so dense light couldn't travel. It was trapped, bouncing around. Then, after about 380,000 years, it cooled enough for atoms to form. The fog cleared, and the light that had been trapped was suddenly set free. That first flash has been traveling for over 13 billion years. We see it today, stretched and cooled into a faint microwave glow. It fills every direction of the sky, the afterglow of creation. This glow is almost perfectly uniform. the same temperature everywhere, but not exactly. When we map it with precision using satellites like Planck, we see it's not smooth. It's a tapestry of tiny ripples, minute variations in temperature. Just millionths of a degree, these are the cosmic seeds, the faint imprints of sound waves from the early plasma. The denser spots in this map are where gravity would later get to work, pulling matter together over eons, forming the first stars, the first galaxies, the vast cosmic web we see now. We are seeing the blueprint for all structure. The patterns in this blueprint are like a cosmic barcode. We can scan it, and it tells us something incredibly specific. It tells us the shape of the universe, that it's flat on the largest scales. It tells us precisely how much ordinary matter is in the cosmos, and it tells us with overwhelming confidence that there must be a large amount of something else. Something providing extra gravity, something that doesn't interact with light, cold, dark matter. The data also points to a repulsive component, dark energy. To make the geometry work, this combination, a cosmological constant for dark energy and cold dark matter, is our standard model, the lambda CDM model. It fits the cosmic microwave background data almost perfectly, almost, because within this success there are tiny cracks. The most famous is a tension about the expansion rate. The rate we measure from the cosmic microwave background, a snapshot of the infant universe, suggests one value. The rate we measure from nearby galaxies and supernova, a snapshot of the modern universe, gives a slightly faster value. They don't quite agree. It's a small discrepancy, but in a field built on precision, it stands out. It could be a systematic error in our measurements. Or it could be the first sign our standard model is missing a piece, that the bedrock evidence itself is hinting at a deeper layer of physics, something we haven't yet uncovered. That disagreement in expansion rates, it's not a small thing. It's a crisis. They call it the Hubble tension, and it challenges the whole cosmic story. The issue is the Hubble constant. This one number tells us how fast the universe is expanding right now. To understand anything about the past or the future, that number has to be exact. And we have two ways to measure it, two brilliant, independent methods. They should match, they don't. One method looks at the nearby universe. We use cosmic lighthouses. Stars called Cepheid variables, they pulse with a regular rhythm. That timing tells us their true brightness. Compare that to how dim they appear, and you can measure their distance very accurately. Then we chain that to nearby galaxies, galaxies that have a special kind of exploding star, a type 1, a supernova. These supernova are even brighter lighthouses. They let us measure distances to galaxies far away. By seeing how fast those distant galaxies are moving away, we get a direct measure of the expansion rate today. That's a local measurement, like measuring the speed of cars right in front of you on the highway. The second method looks back in time, all the way back to the cosmic microwave background. That baby picture of the universe. We take our standard model, lambda CDM, and feed the details of that ancient light into the equations. The model then tells us how the universe should have evolved from that infant state to now. It predicts what the expansion rate should be today. That's a prediction from the early universe, like calculating how fast a runner should be at the finish line, based on a photo of them at the start and a complete understanding of the track. Both methods the work of generations, both incredibly precise, and they disagree. The local measurement from Cepheids and supernova gives a faster expansion rate. The early universe prediction from the cosmic microwave background gives a slower one. The gap is small in percentage terms, but in precision cosmology, it's a chasm. Far larger than any possible error, so something is wrong. Either our local measurements are being fooled by something in our galactic neighborhood we haven't accounted for. Or more exciting, our standard model of the universe is incomplete. That lambda CDM model that fits the ancient data so perfectly might be missing a piece. Maybe dark energy isn't constant, maybe its strength changed over time. Maybe there was a new type of neutrino or some other particle floating in the early cosmos, altering how it evolved. Or could space-time itself have properties we haven't even imagined? This tension isn't just a puzzle, it's an opportunity, a crack in the foundation where new physics might show through. It makes every cosmologist question their basic assumptions. Is the universe simpler than we thought, or is it far, far stranger? The answer is in the tension between two numbers. And in the search to make them agree, the cosmic web is like a fossil record. It holds the shape of the forces that built the universe, and that shape isn't random. If you look out far enough, you see this architecture, a three-dimensional tapestry, threads made of galaxies. At the intersections, you get these dense knots. Massive galaxy clusters, hundreds of galaxies, thousands, all bound by gravity, and these clusters are connected by long filaments. They're like rivers of galaxies, stretching for hundreds of millions of light years. And then between them, the voids, these immense, nearly empty regions, spheres of darkness that can be hundreds of millions of light years across. So the large-scale structure isn't a uniform soup. It's a sponge, a lattice of matter and emptiness. This didn't appear overnight. It evolved over 13 billion years. It started with tiny ripples. In the cosmic microwave background, those were the seeds, and gravity got to work on those seeds, pulling the slightly denser regions together, slowly. Over cosmic time, matter flowed from the emptier areas into the denser ones. The voids emptied out, the filaments grew stronger, the clusters became more massive. It was a story of gravitational collapse, written over eons, but then something changed. Dark energy began to dominate. That repulsive pressure, woven into space itself, started pushing against gravity's work. Think of it like building a sandcastle as the tide comes in. Gravity is your hands pulling the sand together. Dark energy is the rising water, working to smooth everything out. It doesn't destroy what's already built, but it makes it much harder for new structures to grow. It slows the clustering. It puts a brake on the formation of the largest features. And that gives us a new way to test our theories. By mapping the cosmic web in detail, we can measure this tug of war. Projects like the Sloan Digital Sky Survey did that. They pointed telescopes to catalog millions of galaxies. They measured positions and distances. From that data, they built three-dimensional maps of the universe. Maps so vast you can fly through them, and these maps are forensic tools. By studying the distribution of galaxies, how clustered they are, the sizes of the voids, the thickness of the filaments, scientists can measure how fast structure has grown. They can see the imprint of dark energy's braking effect. The patterns in these maps provide an independent line of evidence. They strongly support a repulsive component like dark energy. The growth of structure is too slow, too suppressed for gravity alone. But these maps also offer a deeper test. They let us probe the nature of gravity itself on the largest scales. Does gravity work exactly as Einstein predicted across these 100 million light-year voids? Or do we see subtle deviations? The cosmic web is a natural laboratory. Every filament, every void is a data point, a piece of the puzzle. By reading this fossil record, we're deciphering the history of a battle. A silent universe spanning conflict between the pull that builds and the push that smooths. And the outcome of that battle will determine the final form of everything. Most models treat dark energy as a constant, a steady pressure in the vacuum. But we have to consider a darker possibility. Some theories propose a dynamic form, phantom dark energy. Its density wouldn't stay the same, it would increase. As the universe expands, creating more space, the repulsive force in each new bit of vacuum would be greater than before. The push would grow. It would feed on itself, accelerating not just the expansion but its own strength. A runaway effect, and if that were true, the future of the cosmos would shift from a slow fade to a violent, definitive end. a scenario called the Big Rip. Imagine a force that grows without bound. For billions of years, its influence is subtle, just as we see now, but eventually it becomes the dominant player on every scale. First, it would overcome the gravitational glue holding galaxy clusters together. Those vast cities of galaxies would be pulled apart, their members scattered into the void. Then the force would turn inward. The weaker gravity binding individual galaxies would be next. A galaxy like our Milky Way would be shredded, its stars flung into the growing darkness. As the acceleration becomes unimaginable, it targets smaller structures. Solar systems would be torn from their stars, planets ripped from their orbits. In the final moments, the force would overcome the very bonds holding matter together, the electromagnetic forces that bind molecules, the strong nuclear force that binds atomic nuclei. In a final, catastrophic instant, every atom, every fundamental particle would be torn apart from every other. The fabric of space-time itself would be stretched to a singularity. A terminal rupture. This is a speculative extreme. Current data disfavor this phantom model. Evidence from the cosmic microwave background and large-scale structure surveys points to a cosmological constant. A steady dark energy, but the possibility remains open. That dark energy's strength is evolving, even if slowly. The key is to measure the expansion history with greater precision. Future observatories are designed to do that. The Vera C. Rubin Observatory, the Nancy Grace Roman Space Telescope. They will map billions of galaxies across cosmic time. They're looking for the subtlest changes in how fast the universe was expanding at different epochs, searching for any sign that dark energy is not a passive backdrop, but an active, changing field. The true nature of this mystery component could determine more than just the universe's fate. It could determine its ultimate character, whether it ends with a whisper or with a rip that echoes through nothingness. Empty space isn't empty. That's one of the strangest things you learn. The void between stars, the vacuum between atoms, it's full of activity. Particles and antiparticles flicker into existence. They borrow energy just for a moment, and then they annihilate, they vanish. This quantum foam, this sea of virtual particles, gives the vacuum a background energy. A kind of hum, and for a long time, physicists thought this vacuum energy could be dark energy, a natural property of space itself, like Einstein's cosmological constant. But when they calculated how much energy that activity should create, the result wasn't just wrong, it was a catastrophe. The prediction from quantum field theory was enormous. Unimaginable, it was off by a factor of 10 to the 120th power, a 1 with 120 zeros after it. It's the worst prediction in the history of science. To see what that error means, think about that amount of vacuum energy. If empty space held that much repulsive power, the universe couldn't exist, not even for a second. The expansion would have been instant, violent, no stars could form, no atoms could hold together. The cosmos would have blown itself apart right after the Big Bang. The fact that we're here, that galaxies exist, tells us the real vacuum energy is almost zero, infinitesimal. But our best theory of the small, quantum mechanics, says it should be unimaginably large. This isn't a small puzzle, it's a screaming contradiction. It points to a fundamental gap, the two pillars of modern physics, quantum mechanics for the very small, general relativity for the cosmos, are speaking different languages here. One predicts a universe that should have self-destructed. The other observes a universe that's gently accelerating, so we're left with possibilities. Either our understanding of the quantum vacuum is flawed, missing some principle that brings that colossal number down to nearly nothing, or there's a perfect cancellation mechanism. A symmetry we haven't found yet, where positive and negative contributions balance out to almost zero, leaving behind only the tiny residue we call dark energy. This vacuum energy catastrophe isn't just a technical problem, It's where the mystery of dark energy is rooted. The answer won't be a small tweak. It will require a revolution. A new theory that bridges the chasm between the quantum world and the cosmos. We have to ask if dark energy is really constant, or if it's something that breathes. To get around the vacuum energy problem, physicists have moved past the idea of a simple cosmological constant. They've suggested the universe might be filled with dynamic fields. The leading idea here is called quintessence. You can picture it not as a fixed property of space, but more like a cosmic atmosphere, a fluid that fills everything with a density and pressure that can change over billions of years. The name comes from an ancient term for a fifth element, something beyond earth, air, fire, and water, a heavenly substance. In this model, quintessence is a new kind of field. It could be similar to the Higgs field, the one that gives particles mass, but it works on the largest scale, and unlike a constant, it can evolve. In the early universe, its density might have been higher, its push stronger. Or it might have been dormant, only waking up as the cosmos expanded and cooled. This could explain a deep mystery, why dark energy became the dominant force only around 5 billion years ago. For more than half the universe's history, gravity was in charge. Matter clumped together. Then, as space grew and the density of matter fell, this quintessence field could have emerged from the background, taking over and starting the acceleration we see now. It might even interact weakly with matter, which opens the door to entirely new physics. There are other theories with more exotic dynamics. K-essence, for example, where the field's kinetic energy, its energy of motion, drives the repulsion in strange ways, or models that use extra dimensions of space, where the force we see as dark energy is actually a gravitational leak from a neighboring reality. Each alternative makes a distinct prediction. They forecast how the expansion rate should have changed over cosmic time in a specific pattern. A constant dark energy gives you one curve on the graph of the universe's growth. A dynamic field like quintessence gives you another. The difference is subtle, buried in the light from galaxies billions of light years away. This is where the next generation of telescopes becomes our most powerful tool. The Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope aren't just cameras, they're time machines. They will map the three-dimensional positions of billions of galaxies, building a movie of cosmic expansion across 10 billion years. They'll look for the telltale signature of a changing dark energy. Is the acceleration steady, or is it speeding up or slowing down on its own? The hunt is a process of elimination. Each alternative theory is a different path through a labyrinth. Our job is to see which one, if any, leads to the center, to see if the dominant force in our universe is a static feature of the stage or a dynamic player with its own story still unfolding. Light can be a kind of cosmic spy. It carries information about where it came from and also about everything it passed along the way. That's the power of gravitational lensing. It was a prediction from Einstein's theory, and now it's one of our sharpest tools. Here's how it works. You have a massive object in space, like a galaxy cluster, sitting between us and a galaxy far behind it. The cluster's huge gravity warps the space around it, so when light from that background galaxy comes through that warped region, its path bends. It doesn't go straight. It curves, and from where we are, the image of that distant galaxy can get stretched or magnified, or even split into multiple images. It's like looking through the bottom of a wine glass. The glass distorts whatever's behind it. The cluster acts as a natural lens, a cosmic magnifying glass, and by studying that distortion, we can weigh the lens. We can map where the mass is in that foreground cluster, which includes the huge halos of dark matter around it. That's strong lensing. The effects are dramatic. Beautiful, but there's a subtler version, a more powerful one, weak gravitational lensing. It's not about dramatic arcs or rings. It deals in tiny, statistical distortions. Most background galaxies are only slightly warped. their shapes stretched by a minuscule amount. No single distortion tells you much, but when you survey millions of galaxies across a huge patch of sky, the patterns show up. You see a coherent shearing, a gentle stretching that aligns with the gravitational pull of the large-scale cosmic web. This big statistical map is a direct probe of the distribution of all matter. The seen and the unseen. It's like feeling the shape of an invisible sculpture by running your hands over its surface, but weak lensing does more than just map mass. It's also a probe of the universe's geometry, its expansion history. How much a light ray bends depends on the distances involved. The distance from us to the lensing cluster, and from the cluster to the background galaxy. Those distances are set by the expansion rate of the universe, by its overall geometry. They're directly affected by dark energy, and lensing also measures how cosmic structure grows over time. By looking at background galaxies at different distances, which means different look-back times, we can see how the clustering of matter has evolved, and how the strength of the lensing effect has changed. Dark energy suppresses the growth of structure. It puts a brake on gravity's ability to pull matter together. So by measuring how the lensing signal changes across cosmic time, we're essentially taking the temperature of dark energy's influence. We're watching its repulsive pushwork against gravity's pull, in slow motion across billions of years. This is where the next leap happens. Projects like the Vera C. Rubin Observatory are built to turn this technique into a cosmic movie. Over a decade, it will image the entire southern sky every few nights. It won't just take a snapshot. It will create a time lapse of the universe. By measuring the weak lensing distortions of billions of galaxies at different epochs, it will build a three-dimensional map of matter's distribution and its evolution. This map will be so precise it could reveal if dark energy's strength has changed. It could detect if gravity itself deviates from Einstein's predictions on the largest scales. Every subtly bent ray of light is a messenger, and together they're writing a story we are just beginning to read, a story of an invisible force traced in the warped light of ancient galaxies. A new messenger from the cosmos. It doesn't come as light, it's a ripple in spacetime itself. In August 2017, we caught one of these gravitational waves and saw where it came from. Two neutron stars, each with the mass of the Sun crushed into a city, spiraled together and merged. That collision sent shudders through the cosmos. LIGO and Virgo detected them here on Earth. Then, 1.7 seconds later, telescopes saw a brilliant flash from the same part of the sky. A gamma-ray burst, then an afterglow across all wavelengths. That was the breakthrough. We had the gravitational wave soundtrack and the light show together. That combination gave us something cosmologists had wanted, a standard siren. It's a play on the term standard candle, like the supernova we use for distance. But this is different, more pure in a way. The gravitational wave signal is like a fingerprint. From its shape, how the pitch and strength change as the object spirals. Scientists can calculate the intrinsic power of the collision. They can hear how loud the crash really was. And just like you can tell how far away a siren is by how faint the sound is, they can tell how far away the merger was by how faint the ripples were when they reached us. That gives a direct, absolute distance. It doesn't rely on the cosmic distance ladder and all its assumptions. It's a ruler built from the geometry of spacetime. Then you look through a telescope, you find the host galaxy of the flash. You measure its redshift, how much its light is stretched by the expansion of the universe. Now you have the two key numbers, the true distance from the gravitational waves and the recession speed from the light. Put them together, and you get a direct one-step measurement of the Hubble constant. The expansion rate of the universe, it's a completely independent path to that number. That first event in 2017 gave us a measurement, and it fell between the two conflicting values from local supernova and the early universe cosmic microwave background. It didn't solve the tension, but it proved the method works. That's the promise. Every neutron-star merger we detect with both waves and light is a new, precise data point. As our detectors get more sensitive, we'll catch more of these events farther out in space and further back in time. Each one is a beacon, a single, clean measurement of how fast space was stretching at a specific moment in history. By building a collection of these standard sirens across different distances, we can trace the expansion history of the universe in a new way. We can ask if dark energy has always been constant, or if its push has changed. We can test if gravity behaves exactly as Einstein predicted over these immense scales, as the waves travel for hundreds of millions of years. It's a new sense for the universe. We're not just astronomers watching the light anymore. We're listeners hearing the space-time tremors from the most violent events, and in their echoes, we might finally hear the answer to how fast everything is flying apart and why. That sound left a mark, a kind of fossil echo. Right after the Big Bang, the universe was this hot, thick fluid, a plasma of protons and electrons and light, all mixed together. And in that soup there was a struggle, gravity pulling matter in, trying to make it clump, and then radiation pressure, the force of all that trapped light, pushing it outward. That struggle made pressure waves, ripples moving out from any slightly denser spot, like sound moving through air. For almost 400,000 years, these acoustic waves traveled through the cosmic fluid. That was the first sound, a deep hum. Then something changed. The universe expanded and cooled enough for atoms to form, neutral hydrogen, and suddenly light could travel free. The fog lifted, and right at that moment, those pressure waves just stopped. They froze. The ripples were caught like a photo of a splash stamped into the matter. That left a signature, a specific scale. Think of dropping a pebble in a pond. The ripples spread in a circle. Now imagine the pond froze solid the instant the first ripple hit a certain distance. That distance is the imprint. For the cosmos, that distance is about 500 million light years. It became a standard ruler carved into the universe. We call them Baryon acoustic oscillations, the bow, and we can still see them, not as sound but as a pattern in where galaxies are. When we map millions of galaxies in 3D, it's not just random. We see a slight excess of galaxies separated by that specific scale, that 500 million light-year distance. It's like galaxies are a bit more likely to be found at the crest of those frozen waves. This is our cosmic tape measure, and it's powerful because we know its true size from the physics of the early universe. We know how big the ruler is. So when we look out, we can see how big it appears at different distances, and looking out means looking back in time. So this lets us measure how the universe has stretched over billions of years. If expansion had been slowing from gravity, the apparent size of this ruler would follow one curve. If expansion is accelerating from dark energy, it follows a different curve. The measurements from big galaxy surveys are clear. They show acceleration. The BAO ruler looks smaller in the nearby universe than it should if expansion were slowing. Space has stretched more than gravity alone would allow. This geometric test is independent. It doesn't rely on star brightness or explosion physics. It relies on pure geometry and a fossilized sound wave from the beginning. It confirms a repulsive component. And by combining this ruler with other probes, like the cosmic microwave background and supernova, we can pin down dark energy's properties more precisely. We're using the universe's own frozen vibrations to measure the force that's now tearing it apart. String theory rewrites reality at the most basic level. It says the fundamental building blocks aren't particles, not points. They're tiny strings, and these strings vibrate. Like a violin string, pluck it one way, you get one note. Pluck it another, a different note. Each vibration pattern, each frequency corresponds to a different particle. One pattern is an electron, another is a quark. Another is the photon, light itself. So the universe becomes a kind of symphony, a symphony of vibrating strings, but for the math to hold together, the theory needs more dimensions. More than the 3 space and 1 time we know. It suggests there could be 6, maybe 7, extra spatial dimensions, all curled up, hidden at a scale so incredibly small we can't see them. And the shape of these curled-up dimensions, their topology, that shape dictates how the strings vibrate, which then dictates the laws of physics for that universe. The constants of nature, the strength of gravity, the mass of an electron, they stop being fundamental truths. They become outcomes, results of the geometry. The geometry of those hidden dimensions, that opens up a staggering possibility. If there are many, many different ways for these extra dimensions to curl up, then there could be a vast number of possible sets of physical laws. This is the string theory landscape, a cosmic terrain of maybe 10 to the 500 different possible universes, each with its own unique physics. In this landscape, something like the cosmological constant, our dark energy, it's just another local feature. In some universes, it's huge, causing instant, catastrophic expansion. In others, it's zero, no acceleration at all, and in a tiny, tiny fraction, it has a small, positive value, like the one we observe. So from this view, our universe isn't special by design. It's just one bubble in a multiverse, one valley in an immense landscape where by chance the constants are right for galaxies, stars, life to form. It offers an answer to the fine-tuning problem. We're not asking why the laws are perfectly tuned for us. Instead, we're here because in an unimaginably vast multiverse, a few bubbles will inevitably have the right conditions. We find ourselves in one of the habitable ones. The question shifts. It's no longer why the constants have these precise values. It's why we are in this particular bubble with these particular rules. Now, this landscape idea is compelling, but it's also deeply controversial. Critics say it makes string theory untestable. It moves it from physics into metaphysics. If we can never observe another bubble universe, can we ever confirm the landscape is real? Proponents argue there might be subtle imprints on our own cosmos, maybe in the pattern of the cosmic microwave background. Something for future observations to find. For now, it stands as this breathtaking theoretical frontier, a place where the mystery of dark energy isn't a puzzle to be solved just within our universe. It becomes a clue pointing to a reality far grander and more strange than we ever imagined. The value we measure for dark energy isn't just a number. It's more like a whisper where it could have been a roar. The amount is incredibly small, almost impossibly small. If it were just a little stronger, a little more repulsive, then the story would be over before it started. That initial expansion would have been so violent that matter could never gather, no gas clouds collapsing, no stars igniting, no galaxies spinning into existence. The universe would be a thin, cold void, just an empty expanse stretching on. But if dark energy were negative, if it pulled instead of pushed, the opposite happens. Gravity wins too fast. The universe collapses back on itself in a big crunch, maybe only a few million years in. Again, no time for stars or planets or life. The fact we're here looking out at a structured cosmos means the value had to be in an extraordinarily narrow window, small enough to let gravity work for billions of years, building the cosmic web, but present enough to now be taking over, driving the acceleration we see. This balance is so precise it feels like a staggering coincidence, like the universe balanced on a knife's edge. Tilt one way, everything flies apart into nothing. Tilt the other, everything crushes into a singularity. We're in that narrow sliver where neither catastrophe happened. That's the fine-tuning enigma. To explain it, some point to the anthropic principle. It's a logical idea, even if it's dizzying. The constants are what they are because in a universe where they were different, there'd be no observers to wonder about them. We might just be living in one of the rare bubbles where the numbers lined up right for complexity and life. It shifts the question, not why the universe is fine-tuned for life, but why we find ourselves in one that is. Others see fine-tuning not as an accident but as a clue, a signpost to a deeper, undiscovered law. Maybe there's a dynamic mechanism, a cosmic thermostat, that naturally settles dark energy's value near zero. Or maybe our understanding of the vacuum and its energy is incomplete, and the small value we see comes from a symmetry we don't yet understand. However we approach it, the fine-tuning of dark energy is one of the most profound mysteries. It suggests our universe isn't just any universe. It's a universe uniquely poised across billions of years to allow for structure to unfold, and ultimately for creatures to look up and ask why. There are these clocks out in the galaxy, pulsars. They're what's left after a big star explodes, a neutron star, just a few miles across but heavier than our sun. And they spin hundreds of times a second. They send out beams from their poles like a lighthouse. Every rotation we get a pulse, a radio wave we can catch with telescopes. And the rhythm of it is incredibly steady. For some of them, that ticking is more reliable than our best atomic clocks. That's not just interesting, it's useful. It's a natural lab, a place to test physics under conditions we can't make. We can use them to test gravity. The best tests come from pulsars in pairs. A binary system, when a pulsar orbits another dense thing, another neutron star or a white dwarf, that dance follows gravity's strictest rules. Einstein's theory makes a prediction for a pair like that. As they orbit, they should lose energy. That energy doesn't disappear. It gets carried away by ripples in space-time, gravitational waves, and as the energy leaves, the two stars spiral inward. The orbit decays a little bit. For most systems, that's too small to see, but with a pulsar's clock, you can track it. You measure the arrival time of each pulse. Very carefully, over years, you build a map of the orbit, and you can see if it's shrinking, exactly at the rate Einstein's math says it should. The famous one is the Hulse-Taylor binary. Found in 1974, for decades they watched its pulses. They saw the two neutron stars getting closer. The orbital decay matched the prediction from gravitational waves. It was the first indirect proof those waves existed. Long before LIGO saw them directly, it confirmed general relativity in a place of very strong gravity. Since then, we've found other binary pulsars, each one a new test. Some have a pulsar with a white dwarf, testing how gravity acts with different dense matter. And so far, in every case, Einstein's theory has passed. It holds up, but the search is going further. The ultimate lab would be a pulsar orbiting a black hole. The gravity there is extreme. Space-time is curved to its limit. It's a place where some other theories that try to change gravity or mix it with quantum physics, they predict you might see a tiny deviation. Finding a system like that would let us probe that intense arena. We'd use the pulsar's clock to map the space-time around the black hole with unbelievable precision. Any small shift in the timing, any wobble in the orbit that doesn't fit Einstein's blueprint, that could be the crack, a sign that on the largest scales, the rules might be different. That's how it connects these precise experiments in our galaxy. They're testing the same force that, on cosmic scales, seems to be losing its grip to dark energy. If we found even a hint of modified gravity near a black hole, it would change cosmology. It would suggest the universe's acceleration might not need a mysterious dark energy. It might just need a corrected understanding of gravity, of how it works across the vast, empty spaces between galaxies. Right now, Einstein is still right. But the search goes on, tick by precise tick, listening for any stumble in the rhythm. The next step is already happening. It's in the mirrors and sensors of new observatories in space and on the ground. Their job is to turn questions about dark energy into a flood of data, so much data it could break the stalemate. The Nancy Grace Roman Space Telescope is leading that. It's set to launch in the next few years. It'll survey the cosmos on a staggering scale. It'll hunt for distant supernovae. It'll measure the subtle distortions from weak gravitational lensing across billions of galaxies. It'll map the frozen sound waves of Baryon acoustic oscillations, and it'll do all that with a field of view 100 times larger than Hubble's. The goal is to measure the expansion history and the growth of cosmic structure with a precision we've never had. Meanwhile, the European Space Agency's Euclid spacecraft is already on its way. Its specific job is to map the geometry of the dark universe. By observing billions of galaxies out to 10 billion light-years, it will create the most extensive 3D map of the cosmos ever. That map will chart the influence of dark matter and dark energy on how structure evolves. It's looking for the subtle imprint of dark energy's push on the shape of everything. Back on Earth, in the mountains of Chile, the Vera Sea, Rubin Observatory is getting ready for a different kind of watch. Its legacy survey of space and time won't take just one snapshot. Over 10 years, it will image the entire southern sky every few nights. That creates a time-lapse, a dynamic movie of the universe. It'll track the motions and brightness changes of billions of objects. For cosmology, that repeated all-sky view changes everything. It lets scientists measure weak lensing and galaxy clustering with a statistical power that's almost like a new sense. They'll see the cosmic web not as a static picture, but as something that evolves. The data from these projects will be measured in petabytes, a volume of information that's hard to grasp. But inside that digital ocean will be a detailed three-dimensional film. A film of the universe's expansion and the growth of its structure over the last 10 billion years. That's our best hope. By comparing how the universe has stretched and how matter has clumped together across cosmic time, these observatories can run a critical test. They can distinguish with high confidence between a simple, unchanging cosmological constant and a dynamic field like Quintessence. They could even find evidence so strange it points not to a new energy, but to a fundamental change in gravity itself. We're building the instruments that will finally let the universe answer. We need a laboratory for these questions, but there's only one universe, so scientists build their own. They create entire cosmos inside supercomputers. These are cosmological simulations like Illustris TNG or the Millennium Project. They start with a simple grid. A sparse digital space set up to match the smooth, hot early universe after the Big Bang. Into that void, they pour the laws of physics, gravity's equations, Newton's, Einstein's. The hydrodynamics of gas, the complex steps of star formation, supernova explosions, and they include their best models for what we don't see, vast halos of cold dark matter, and the smooth, repulsive pressure of dark energy. Then they press start. The simulation runs forward in time. It calculates the gravitational pull between trillions of particles. Slight over-densities grow under that pull. Gas cools, collapses into swirling disks, galaxies form. They merge, they're torn apart. Over billions of simulated years, a full cosmos emerges, a virtual universe with its own web of filaments, clusters, voids. The result is a digital tapestry, eerily similar to what we see through telescopes, but the real power isn't in making a copy, it's in changing the rules. They can run the experiment again, but tweak one parameter. What if dark energy were twice as strong from the start? They adjust the code, run a new universe. In that simulation, the repulsive push overwhelms gravity much earlier. Galaxies never form properly. The cosmic web stays faint, wispy, a ghost of our own structured reality. That simulated universe would be cold, empty. It doesn't match observations, so that extreme model is ruled out, or they test modifications to gravity itself. Alter the equations so gravity behaves differently on the largest scales, trying to mimic dark matter or dark energy without including them. They run that simulation forward, examine the resulting galaxy clusters. Do the virtual galaxies rotate like real ones? Is the clustering of matter over hundreds of millions of light years a match? Usually, these alternative gravity simulations produce a universe that looks off. Galaxies might be the wrong shape. The vast voids might be too large. The simulated cosmos fails the eye test against our real one. This process turns cosmology into a testing ground. Simulations let researchers play what if with fundamental laws. They explore consequences of different theories in a controlled, repeatable way. They help identify subtle observational signatures, specific patterns in how galaxies are distributed, precise statistics of weak gravitational lensing. That would be the fingerprints of a changing dark energy or modified gravity. They tell astronomers exactly what to look for in the next sky surveys. So these vast digital universes become a bridge. They connect the abstract math of theory to the concrete, messy data of observation. They're our best tool for interrogating the shadows, for asking the cosmos a question and seeing in a universe of our own making what the answer might look like. The equations describe a process, but the conclusion is unsettling. If the acceleration continues, the future isn't just fading, it's profound isolation. Over trillions of years, a boundary forms around our corner of the universe, the cosmic horizon. Space stretches faster. Distant galaxies get carried away so fast their light can't cross the gulf to reach us. They won't vanish in a flash, they'll fade from view one by one, their light stretched beyond detection. Eventually, every galaxy outside our own local group, the few dozen bound to the Milky Way, disappears over that horizon. To any future civilization here, the observable universe shrinks to a tiny, lonely island. The sky, which blazes now with evidence of a vast cosmos, goes dark. The cosmic background radiation, that ancient afterglow, redshifts into silence. The universe becomes a cold, empty expanse, increasingly lonely. This is the ultimate heat death, accelerated and made absolute by dark energy. This vision carries a heavy weight. It challenges our sense of place. We find ourselves alive in a remarkably brief, golden epoch. A sliver of time after the first stars ignited, but before the accelerating expansion erases the celestial tapestry. We live in a universe that's still transparent, still richly structured, still filled with the light of distant suns. Matter has clumped into galaxies and planets. Conditions for life have arisen. Curious minds can look up and trace the story of creation itself. We are here at the precise moment when the cosmos is knowable. That timing feels significant, yet the forces driving this story remain almost entirely mysterious. The acceleration puzzle is more than a scientific challenge. It's a humbling mirror. It reflects the extraordinary power of human curiosity, our ability to measure the expansion of the universe, and it reflects the vast, sobering depth of our ignorance. We've built civilizations, unlocked the atom, sent probes beyond our solar system, yet we don't know what constitutes 95% of reality. We're deciphering a cosmic fate written in a language we're only beginning to learn. This isn't a reason for despair, it's for a deeper kind of wonder. Our brief moment of cosmic awareness becomes all the more precious. The questions we ask today, the maps we're making of the dark universe, they are a testament to a profound urge to understand our home, even as its ultimate fate drifts towards silence. The accelerating expansion frames our existence not as the center of the story, but as a fleeting, brilliant chapter. A chapter within an epic of almost unimaginable scale and duration. And in that framing, the very act of asking becomes the most human response. A response to the vast, dark mystery unfolding around us. Dark energy takes us into a different world. The world of the very small, because the answer might not be out there in the cosmos. It might be in here, in the particles. The whole universe could be shaped by fields and particles we studied deep underground. The main idea for dark energy is called quintessence. It's imagined as a new kind of field everywhere in space, a scalar field. That's a field with a value at every point, like a temperature. We already know one of these, the Higgs field. It gives particles their mass. Particles move through it, they interact, and that interaction is mass. Finding the Higgs boson was a huge deal. It proved this field exists, this sort of cosmic molasses filling the vacuum. So quintessence would be another field like that. But with different properties, one that doesn't give mass. Instead, it pushes on space itself. A gentle, repulsive pressure. That's why particle accelerators matter for cosmology. When we smash protons at near light speed, we're making the conditions of the early universe. We're reaching energies where new things might show up. A new particle, a tiny anomaly in how particles behave, that could be the first clue. A microscopic hint that, when you scale it up to the whole cosmos, becomes the accelerating expansion. Dark energy, it's a dialogue. Astronomers see the large scale affect the what. Particle physicists look for the tiny mechanism, the how, but the connection is deeper than that. Dark energy is really a crisis of unification. Our two best theories don't fit together. General relativity describes gravity, the cosmos. Quantum mechanics describes the subatomic world. They're both incredibly successful, but they don't speak the same language, and dark energy sits right where they collide. The vacuum energy catastrophe proves it. Quantum theory says the vacuum should have immense energy. We see almost none. That's the screaming proof of the divide. So solving dark energy probably means building a bridge. A theory of quantum gravity. One framework for the force that holds planets and the forces in atoms. Whether it's string theory, loop quantum gravity, something else. It has to give us a universe with a cosmological constant as tiny as ours, or it has to explain a dynamic field like quintessence. So this isn't just an astronomy problem. It's a central challenge for all of physics. It forces us to think about the farthest galaxies and the nature of the vacuum, the birth of particles, the geometry of reality. The answer will be written in both languages, the cosmic web and the quantum foam. History repeats its mysteries. A century before dark energy, there was another ghost in physics, the luminiferous ether. In the late 1800s, scientists were sure light needed a medium to travel, like sound needs air. They pictured this invisible, frictionless substance filling all of space. The ether, it was elegant, it seemed logical, it felt necessary. Then came an experiment to find it. Albert Michelson and Edward Morley built this delicate device to measure the Earth moving through that cosmic sea. They expected a shift, a drag, some whisper of the ether's flow. They found nothing. It was a profound null result, a stunning silence. That failure didn't just disprove the ether. It broke a foundational assumption. It created a crisis, and from that crisis, a young patent clerk, Albert Einstein, offered a revolutionary answer. Special relativity. He showed light needed no medium. The speed of light was constant for all observers. Absolute space and time had to be abandoned. That elegant placeholder, the ether, was swept away by a deeper, stranger truth. Today, we feel a similar tension. Dark energy is our modern ether. An elegant placeholder to explain a profound anomaly, the accelerating expansion of the universe. It fits the data. It holds our equations together, but like the ether, it's inferred. Not directly touched, we see its shadow in the galaxies receding, just as physicists once felt the ether's necessity in the behavior of light. The parallel raises a humbling question. Are we on the brink of another Michelson-Morley moment? Is a future experiment, a more precise map of the cosmos, destined to find a null result? One that forces us to abandon dark energy for a deeper theory. Or is dark energy fundamentally different, a real component of reality, waiting for its direct confirmation, like the Higgs field after decades? The story of the ether teaches a lesson in scientific humility. Sometimes our most logical, beautiful constructs aren't discoveries of final truth. They're signs, signposts pointing toward a coming revolution. They're the best explanations we have until the anomaly grows too loud to ignore. The ether wasn't a mistake, it was a necessary step, a framework that held the data until a genius saw a path through the contradiction. We're in that same state of productive uncertainty. The anomaly is the accelerating universe. Our elegant placeholder is dark energy, or maybe a modification to gravity. Our Michelson-Morley experiments are the next-generation telescopes, the gravitational wave detectors. Gathering data with unprecedented precision, probing the shadow, listening for its nature, they may confirm the placeholder as reality, or they may find a subtle inconsistency. A crack in the model, something that forces a conceptual leap we can't yet imagine. This historical echo isn't a reason for doubt, it's a reason for awe. It means we're participating in the same essential process that has always driven science forward. We're confronting the anomaly. We're living through the tension before the paradigm shifts. And that's where the most exciting discoveries are always made, in that quiet, persistent struggle to understand a universe that refuses to conform to our comfortable stories. The sheer volume of data is a new frontier. These next sky surveys, they're not just more pictures, it's a flood of information. It's beyond what we can really grasp. The Vera C. Rubin Observatory, for example, it will collect over 20 terabytes of data every night. That's like streaming thousands of high-definition movies. Every single night, and it does that for 10 years. And in that ocean of numbers, the signals we're looking for the exact shape of a galaxy, the light from a supernova, they're like single grains of sand. Finding them by hand is impossible, so the search needs a new kind of partner, not a telescope, an algorithm. Machine learning and AI are becoming essential. These algorithms are trained. It's like teaching a child to recognize shapes. Scientists give them millions of labeled examples, images of galaxies warped by gravitational lensing. Light patterns from known supernova. The AI learns the fingerprints, and once it's trained, it can scan new data incredibly fast. It can flag a potential supernova minutes after detection. It can measure the warped shapes of millions of galaxies for weak lensing maps. It does this with a consistency beyond human ability. It removes human bias. It removes fatigue, but its role is bigger than just identification. The real power is in pattern recognition, on a scale we can't perceive. Hidden in the relationships between billions of data points, the positions, the colors, the shapes of galaxies across time. There could be subtle correlations. Patterns that encode the precise behavior of dark energy. A machine learning model built to find hidden structures could uncover a signal too faint and too complex for any human to ever see. It might find a connection between how galaxies cluster in one era and the expansion rate in another. A connection that points decisively to a dynamic form of dark energy. Or even a flaw in our gravity equations. This synergy extends to the supercomputer simulations too. Scientists can have an AI run a vast ensemble of virtual universes, each with slightly different physics, different strengths of dark energy, different modifications to gravity. The AI then compares each simulated universe to our real observational data. It searches for the best match. It can explore this immense parameter space, this landscape of possible laws, with an efficiency no human team could match. So cosmology is being transformed. It's becoming a deeply data-driven science, where the path to discovery is paved by algorithms sifting through the digital echoes of the cosmos. The key to the expansion puzzle might first spark to life not in a moment of human insight under a starry sky, but in the silent, intricate connections of a neural network. Finding a story in the numbers we ourselves wrote down but could not read. These galaxies are like clocks, ancient ones, not the bright, star-making spirals you might think of. They're the other kind, massive, red, quiet, elliptical galaxies. They formed in a huge burst way back at the beginning, then they settled, stopped making stars. And they've just been aging since for over 10 billion years. All their stars are like one generation, born together, growing old together, so astronomers can look at their light and figure out how old they are. They check the spectrum, look for certain signatures, the dimming of specific elements, the overall reddening that tells you when those stars formed. The galaxy itself becomes a chronometer, a clock that started at its birth. The method works by comparison. You find these massive, quiet galaxies at different distances. One galaxy's light took 10 billion years to get here. That's a snapshot of the universe at that younger age. You measure its stellar age. Maybe it was 1 billion years old back then. Then you look at a similar galaxy closer to us. Its light took, say, 8 billion years. You measure its age then. Maybe it's 3 billion years old at that later time. The difference in their ages, 2 billion years, that's how much actual cosmic time passed between those two snapshots. It's direct. It doesn't depend on supernova models or sound wave physics. You're reading time straight from the stars. Then you take that elapsed time and compare it to the redshift difference between the galaxies. That lets you calculate the expansion rate of the universe during that specific slice of history. They call that h of z, the Hubble parameter at a given redshift. It gives you 1 point on the expansion graph. Do this with galaxies at many distances, and you build a timeline. A direct record of how fast space was stretching over time. This cosmic chronometer is independent. It doesn't assume a particular model for dark energy or gravity. It's a clean check on the story from supernova and the cosmic microwave background. So far, the results line up with an accelerating universe. They support the standard model. But the precision is getting better. Telescopes like James Webb are looking deeper. They'll find these quiet galaxies even farther away, push the chronometers further back. The goal is to see if the expansion history from these aging stars matches the lambda CDM prediction perfectly. Any small deviation in the timeline, a period where the universe expanded a little faster or slower than expected, that would be a huge clue. It could be a sign that dark energy changed strength, or that gravity behaved differently in the past. In the quiet, red light of the oldest galaxies, we're learning to read cosmic time. To understand the push, you have to look at the pull of nothing. Cosmologists usually map the bright knots of galaxies, but now they're looking at the opposite. The cosmic voids, these are the emptiest places, spheres of near-nothingness stretching for hundreds of millions of light-years. Inside, maybe a handful of lonely galaxies drifting in darkness. These voids aren't just empty space, they're dynamic, and they hold a key to the acceleration. Think of the universe as Swiss cheese. The cheese is the cosmic web, the filaments and clusters, rich with matter. The holes are the voids. In the cheese, gravity is strong. It's complex, messy. The signal is loud, but inside the holes, it's quiet. The gravitational pull from matter is minimal. It's a clean laboratory. In that quiet, any subtle effect like the gentle push of dark energy or a slight deviation from Einstein's gravity should be easier to detect. In the crowded cities of galaxy clusters, a whisper is lost. In the silence of the voids, you might hear it. The behavior of these voids over time is a direct test. In our standard model, with dark energy as a constant, voids expand. They get emptier as galaxies are pulled out toward the denser walls. The rate of that expansion, the way a void's shape evolves, is predicted by our equations. But some alternative theories, ones that modify gravity, make a different forecast. They suggest that in these underdense regions where the gravitational field is weak, the modified force could cause voids to expand faster, to become larger or more spherical than general relativity would allow. So scientists are using massive galaxy surveys now to do more than find galaxies. They're mapping where they are not. They're drawing the boundaries of these great cosmic deserts. By measuring the shapes and sizes of thousands of voids across different cosmic epochs, they can watch how these empty regions have grown over billions of years. They can compare that growth to the predictions of different models. This void perspective flips the script. Instead of focusing solely on the builder's gravity pulling matter together, we're studying the smoothers, the force that works to empty out the cosmos. Dark energy is the ultimate smoothing agent. By measuring how effectively voids are being carved out and stretched, we're taking a direct measure of its repulsive work. Every vast, empty region is a fossil imprint of the push that's winning. And in the profound silence of these great nothings, we might finally hear the clear voice of the force that fills the universe. Any new idea has to walk a kind of tightrope. It has to explain something big, like why the universe is accelerating, without breaking everything else we know. You could propose a change to gravity, a new equation, but that equation can't just work for galaxies moving apart. It also has to pass every other test gravity has already passed. It still has to predict the exact wobble in Mercury's orbit, the one Einstein explained. It has to get the bending of starlight around the sun exactly right. It has to match the slow, perfect spiral of binary pulsars timed over decades. If it fails even one of these local tests, it's probably wrong. The universe isn't a bunch of separate puzzles. It's one system. The rules for a galaxy cluster have to work for a planet too. That consistency is a ruthless filter. It's eliminated a lot of clever ideas. Some modified gravity proposals, for instance, they introduce ghosts, not spirits but instabilities, mathematical phantoms that would make the theory predict impossible things, like negative probabilities or runaway energy. That's a sign of a flawed foundation. A good theory has to be robust, mathematically healthy from the smallest scale to the largest. The same strict logic applies to dark energy ideas. If it's a new field, something like quintessence, it has to play nicely with the known fields of particle physics. It shouldn't produce strange, unseen particles in our colliders. It shouldn't violate fundamental energy conditions in a way that would break causality or allow time travel. Its influence has to be subtle enough to have lain dormant for billions of years, only becoming dominant when the universe became large and sparse. Building a theory that ticks all these boxes is extraordinarily hard. That's why the cosmological constant, for all its mystery, is still the simplest fit. It's a single number, a constant. It doesn't change, it doesn't interact, it just is. It modifies Einstein's equations in the most minimal way. It doesn't require new particles or forces that mess with well-tested physics here on Earth. It's an elegant placeholder that so far doesn't break anything else, but its tiny, fine-tuned value is the profound puzzle. So the search isn't just for an idea that fits the new cosmic data. It's for an idea that weaves into the entire tapestry of physical law. The right explanation will feel inevitable. It will resolve the universe's acceleration while leaving the rest of our understanding not just intact, but maybe even more deeply connected. We're looking for the missing piece that makes the whole picture clearer, not one that forces us to tear the rest of it down. Every step across this tightrope is watched by the entire body of physics. And the net below is very, very far down. The galaxies on your screen need a human eye. They need yours. For more than 10 years now, a project called Galaxy Zoo has been asking people to do something. To look at images of galaxies, distant galaxies, and help classify them. Is it a spiral, an elliptical? Is it a merger? That simple act of looking, done by hundreds of thousands of people, has built a catalog. A massive catalog verified by humans, and that catalog is gold for cosmology. It's the foundational data, the data that trains the algorithms that measure weak gravitational lensing, that subtle warping of light that maps dark matter. That maps dark energy, so when you classify a galaxy, you're not just looking at a picture, you're calibrating an instrument, a key instrument in the biggest detective story there is. You are helping to weigh the universe. This is citizen science, and now, with the data coming from telescopes like Vera C, Rubin, the public's role is only going to grow. No army of professional scientists could ever scan all those images, billions of galaxy images, but a global community can, a community of curious people. They can spot the odd things, the rare events, the subtle patterns an algorithm might miss. They become partners in discovery, and this collaboration, it does more than process data. It builds a bridge. It takes the language of cosmology, abstract, intimidating, and turns it into an experience, a personal one. You're not just being told the universe is accelerating. You're helping to measure that acceleration. Sharing these puzzles, it does something. It doesn't just communicate facts, it shows the scientific process. The real process, a collective struggle, a stumbling, brilliant struggle against not knowing. It shows that science isn't a list of answers in a book. It's a living thing. It's about confronting uncertainty, monumental uncertainty. It's about proposing ideas, wild ideas, and testing them against data. And having the humility to be wrong. It's about a community, PhDs in labs, volunteers at kitchen tables, all pulling in the same direction. To engage with the dark energy puzzle is to join an adventure. One of humanity's grandest, it connects a simple act, clicking on a galaxy, to the fundamental fate of everything. The quest to understand the expanding universe, it's a shared endeavor. It ties that basic wonder, looking up at the stars, to the farthest reaches of space and time. It reminds us the story of the cosmos is, in part, our story to tell. In the very beginning, there's a theory that says the universe did something astonishing. It didn't just expand, it exploded outward faster than you can imagine. In less than a trillionth of a second, a region smaller than an atom inflated to become larger than everything we can see. That's cosmic inflation. And it was driven by a repulsive energy field, like a supercharged version of what we now call dark energy. Inflation's job was to smooth everything out, to iron the wrinkles from spacetime, to make the universe uniform on the largest scales, which is exactly what we see. Then, its fuel spent, that field decayed. The violent inflation ended, and the more sedate, matter-dominated expansion of the Big Bang took over. Now, fast forward nearly 14 billion years. The universe is vast and cold, and expansion is speeding up again, this time driven by the gentle, persistent push of dark energy. The scales are incomparable. The energy density of the inflationary field was unimaginably higher, but the parallel is striking. Both are episodes where the fabric of space itself is commanded not by matter, but by a dominant, repulsive energy that causes accelerated expansion. One sculpted the infant universe, the other is determining its final fate. This echo has led physicists to wonder, could they be connected? Is dark energy, in some way, the ghost of inflation? A remnant of that primordial field that never fully went away? Or perhaps it's a sign of that field waking up again, in a vastly weakened state, after eons of dormancy. Some theories attempt this link, proposing a single underlying substance that can manifest in different strengths across cosmic history. Studying the detailed imprint of inflation, frozen into the cosmic microwave background, might give us hints about how such fields behave. How they transition, how they interact with space-time, clues that could apply to dark energy today. The analogy is powerful. It frames the entire history of the cosmos as a story bookended by acceleration. A violent creative burst at the dawn, and now a slow, patient unraveling at the twilight. Understanding the mechanism behind the first great push might just be the key to deciphering the nature of the last. We listen with everything we have. Light tells one part, the ripples in space-time tell another. A ghostly particle might whisper something else. We're in the era of multi-messenger astronomy now, where one cosmic event speaks in several languages. That neutron star merger, the one that shook space-time and lit up the sky, that was a preview. The gravitational waves gave a pure distance. The light from the collision gave the redshift, the expansion speed right then. The gamma-ray burst gave the details of the impact, the extreme physics. One cataclysm, but three lines of evidence, all converging on one point in the cosmic map. This convergence is powerful because it cancels out assumptions. Each messenger has its own error, its own bias, but when they all agree, when they point to the same expansion history, confidence soars. The error bars shrink, the picture gets sharp, the future network will be vast. Next-generation gravitational wave detectors, like the Laser Interferometer Space Antenna, will listen for mergers of massive black holes from the dawn of time. And fleets of telescopes on the ground and in space, from radio to gamma-ray, will be on standby, ready to swivel and catch the flash. We'll catch these events not as rare surprises, but as routine beacons. Each one a standard siren ringing out, and we may add new messengers to the chorus. Ultra-high-energy neutrinos, for instance. These nearly massless particles travel in near-perfect straight lines from the most violent accelerators. They could point directly back to their source, offering another, completely independent path to measure distance, to probe the space in between. By weaving these threads together, light, waves, particles, we build a robust, multidimensional map of cosmic expansion. We can ask profound questions. Does dark energy affect the journey of a gravitational wave exactly the same way it affects a photon? Do these different messengers, born in the same fire, tell a perfectly consistent story about the stretching of space between there and here? Any discrepancy, any tiny crack in that consistency, would be a revolutionary signal. It could mean our understanding of gravity or particle physics needs a tweak across billions of light years. Or it could reveal that dark energy interacts differently with different forms of energy. This interconnected web transforms cosmology. It moves us from inferring the universe's history from scattered, static snapshots to watching it unfold in real time through multiple, simultaneous senses. We're no longer just astronomers, we're universal translators learning to understand the full conversation. The accelerating universe is a profound lesson about science. It's not just a research topic, it's a classroom. It shows science as it really is, not a settled set of facts, but a living process. A story that's still unfolding, where the biggest questions are open. For a student, that changes things. Instead of memorizing planets or cell parts, you see the scientific method in its purest form. You can follow the steps. Astronomers made an observation: the expansion is speeding up. They formed hypotheses. Is it dark energy, or is our theory of gravity wrong? From those ideas, they made predictions. If dark energy is constant, the cosmic web should look one way. If gravity is modified, it should look another. Then they built the tools to test those predictions, telescopes like Roman and Rubin. That's the entire cycle of science playing out on the grandest stage. It connects dots across the curriculum. The same physics that describes a ball falling also governs galaxies billions of light years away. Einstein's mathematics finds its ultimate test in the emptiness between superclusters. This puzzle bridges the forces studied in a high school lab to existential questions about our place in the cosmos. That connection can light a spark. It can turn a casual interest in space into a passion for engineering or computer science or theoretical physics. It shows that the skills being learned, critical thinking, problem solving, mathematical reasoning, are the very tools being used to map the unknown 95% of reality. Most importantly, this unsolved mystery teaches a humbling truth. It shows that not knowing is not a failure. It's the starting point for all discovery. By grappling with a question even leading cosmologists can't answer, students learn that curiosity is more valuable than certainty. They learn that the most exciting phrase in science isn't "Eureka, I found it," but "That's funny, that doesn't make sense." The universe still holds wonders their generation will be the first to see and name and understand. Their curiosity will build the next great observatory. Their questions will one day solve the puzzle we are only just beginning to trace. This reality that's speeding up, it's already changing the stories we tell. The fate of the cosmos, this vast cooling, it's not just a calculation, it's a canvas, and artists are starting to paint it, writers are weaving it in. You might see installations in galleries, light that's spreading out, sculptures that hold that tension between intricate connection and the inevitable drift. The themes are deep: isolation on a cosmic scale, the fragility of any structure against an entropic tide, that search for meaning in a universe that seems to be forgetting itself. These works, they're not illustrating equations, they're translating feeling. They take the emotional weight of a scientific idea and process it through a human lens. So the abstraction of dark energy, you can feel it in your bones. Science fiction has always played with these ideas, but the frame is shifting. The old space operas, they imagined a galaxy forever bustling, an empire connected for millennia. Now, newer stories grapple directly with the accelerating expansion. They show civilizations watching their cosmic neighborhood shrink. The lights of other galaxies blinking out one by one beyond a horizon you can't reach. These narratives ask what it means to build a legacy, to seek connection when the very stage of the universe is being pulled out from under you. They ask how identity changes when your world becomes an island in an ever-darkening sea. This cultural reflection, it's not a side note, it's a vital part of the discovery. Science gives us the what, the data, the graphs, the models, but art and story, they help us process the so what. They let us sit with the implications. To explore the human dimensions of a cosmos run by a mysterious, repulsive force, they make the science resonate somewhere pure data can't reach. So the puzzle of dark energy becomes more than a technical challenge for astronomers. It becomes a catalyst, a spark for creative expression that examines our place, our time, our yearning for significance against the backdrop of an expanding void. Our exploration of the cosmos has always been dual, a journey outward with telescopes and a journey inward with metaphor. The accelerating universe binds these paths together. It reminds us that every new chart of distant galaxies is also a mirror, reflecting our own hopes, our fears, that relentless need to find beauty and understanding. Even in the gathering dark, the great dream of physics is to find a single, unifying story, to take what we have, the quantum world, the cosmos, all the dark components, and weave them into one seamless whole. A theory that doesn't just patch over the cracks, but explains why the cracks were there to begin with. That's the quest, a new cosmological synthesis. Imagine tracing a single line of logic, from the subatomic frenzy of the Big Bang all the way to the serene, accelerating vastness we see now. A framework where cosmic inflation, dark matter, dark energy, they aren't separate mysteries we invented. They become natural outcomes, predicted, different faces of the same underlying reality. A theory like that would answer the deepest whys. Why did the universe inflate so perfectly at the start? Why is there 5 times more invisible matter than visible matter? And then, most pressingly, why does empty space have this specific, tiny, repulsive energy? A cosmological constant so small it seems like a cosmic afterthought, but so consequential it dictates the fate of everything. A true synthesis would make that strange number inevitable. It would emerge from the mathematics, not be awkwardly inserted by hand. and it would resolve tensions like the Hubble constant discrepancy, not as errors but as clues. Clues we just hadn't interpreted correctly within the larger picture. So where does a theory like that come from? The most promising path goes through the greatest unsolved problem, quantum gravity. We need a theory that marries the rules of the very small with the geometry of the very large. String theory, loop quantum gravity, these are attempts at that marriage. Frameworks built to describe reality at its most fundamental level, where space and time themselves might break down and be rebuilt. The hope is that within these frameworks, a universe like ours with its specific history, its specific dark ingredients isn't an accident. It's a natural possibility or even a necessity given the fundamental laws. We're living in the prelude to that synthesis. This current crisis in cosmology, with its conflicting measurements and placeholder names for 95% of reality, it's not a sign that science is broken. It's the opposite. It's the signal that we're on the verge of a leap. Every great revolution in understanding is preceded by this kind of tension, when the old framework groans under new, inexplicable data. That's when the ground is most fertile for a new idea. The accelerating universe is our beacon. Its light, stretched and reddened, is more than a measurement of recession. It's a question written across the sky, a question that challenges the bedrock of our physical theories and demands a more complete story. So by chasing this puzzle, by mapping its effects with greater precision, we're not just cataloging the demise of the cosmos. We're following clues toward a deeper, more unified understanding of reality. The darkness we're trying to illuminate may ultimately reveal the hidden architecture of everything. 95% of reality is a mystery. That fact should fill you with awe. We've gone from a simple, static sky to a cosmos in flight, from a universe ruled by gravity to one dominated by a repulsive whisper. Something we can't see or touch. We followed the clues, the stretched light from supernova, the frozen ripples of ancient sound, the warped paths of starlight. And every observation points to the same thing. Our understanding is incomplete. The cosmos is playing by rules we haven't fully read. That's the humbling beauty of this moment. We're not at the end of knowledge, we're at the edge of a new map, and the territory ahead is vast. It's dark, but that darkness isn't an emptiness, it's an invitation. To build better telescopes, to write bolder equations, to think in ways we haven't imagined yet. The solution to this puzzle won't come from one mind or one instrument. It'll come from a global collaboration, astronomers at their lenses, physicists at their blackboards, engineers building detectors deep underground, even curious people at home classifying galaxies on a screen. That's how we push back the unknown, together. Whether the final answer is a new substance in the vacuum or a fundamental rewrite of gravity itself, its discovery will be a revolution. It will reshape our story of the universe, from its fiery birth to its ultimate fate. It will redefine our place within it. So remember this, you are here now. In this brief, brilliant sliver of cosmic history, the lights are still on, the questions are still big. This is the golden age of not knowing, and that is the most exciting place to be.